Good afternoon, students. In continuation with properties of real number part 5, I am going to discuss further properties of real numbers. So let us see. First, definition. Absolute value of a real number b is denoted by mod b. This symbol is called mod and is defined by mod b is b if b is greater than 0. 0 if b is 0 means absolute value of 0 is 0, and negative of b if b is less than 0. That is, for example, the modulus of minus 5 will be equal to minus of minus 5, because this minus 5 is less than 0, this is equal to 5. So, modulus of 5, this 5 is greater than 0, this is equal to 5. So, on the basis of this, next theorem 9, if a and b are real numbers, then first mod of a into b is equal to mod of a into mod of b, means absolute value of product of ab is product of the absolute values of a and b. Then mod of a square is square of a, that is, if I simply square the real number or square its absolute value, then the result will not change. If c is greater than or equal to 0, then mod of a is less than or equal to c. If and only if minus c is less than or equal to a, less than or equal to c. That is, if mod a is less than or equal to c, then minus c is less than or equal to a, less than or equal to c. Conversely, if minus c less than or equal to a, less than or equal to c, then mod of a is less than or equal to c. And the last one is minus mod of a is less than or equal to a, less than or equal to mod of a. So let us prove first part of the theorem. Proof. First part. To prove mod of AB is equals to mod of A, mod of A. Case first, if A is 0 or B is 0. If A is 0 or B is 0, then this left hand side is 0. Because multiplication of 0 with 0 is 0, and I have earlier defined mod of 0 is 0. So if A is 0, then this is 0. If B is 0, then this is 0. So the result is trivially equal. So left hand side so the result is true. That is, if either A or B or both are 0, then the result is true. Case 2. If A and B are positive. If A and B are positive, it implies mod of A is A, mod of B is B. Also A and B are positive. Earlier we have discussed that product of two positive real numbers is positive. It means A into B is also positive, because A positive, B positive, therefore A into B is positive. And again, by definition, it implies absolute value of AB is equals to AB. Now this can further, this A equals to mod of A and this B equals to mod of B. So this proves the result for if A and B are both positive real numbers. So case third, suppose A is negative and B is positive. Now A is negative, so by definition mod of A is equals to minus mod of A and mod of B is equals to B, because B is positive real number. Again, we know that product of a negative real number and a positive real number is negative, so it implies A into B is negative, so it implies mod of AB is equals to, by definition of absolute value, mod of AB equals to minus AB, so this can be written as minus A into B. So this minus A is mod of A, B is mod of B. So again this proves itself. Case fourth is similar. If this is positive, this is negative, Now I will discuss when both the numbers are negative. The next case, A less than 0, B less than 0. It means mod of A is minus A, mod of B is minus B. Further, we know that product of two negative real numbers is always positive real number. So A into B, A negative, B negative, the product is positive. So AB is positive. So it implies A into B is equals to AB. This can be written as because if A and B are negative, then minus A and minus B are positive, and product of two positive real numbers is positive. Here AB is positive. So this is equal to mod of A into mod of B. Minus A is mod of A, minus B is mod of B. So this proves the result. Next, second part, mod of A the whole square is equals to A square. Mod of A square. We have to prove that mod of A the whole square is equals to A square. Now, if A is 0, then the result is obvious. Because both sides we get 0, so result is trivially true. If A is non-zero, we know that square of every non-zero real number is positive. It implies A square is positive. So if A square is positive, it implies A square is, because from the definition of absolute value, if A is positive real number, then A is equals to mod of A. So here A square is mod of A square. So this can be written as A into A. Now by first part, mod AB is mod A into mod B. So this is mod A into mod A. So means mod A the whole square. So this proves the second part of the theorem. Next, third part. We shall prove the third part. If C is greater than or equal to 0, then mod A is less than or equal to C. If and only if minus C less than or equal to A, less than or equal to C. So first prove the third part. Suppose mod A less than or equal to C. So case first, A greater than or equal to 0. So by definition of absolute value, mod of A equals to A. So it implies, let us call it inequality 1. Put in 1. So we get A less than or equal to C. Case 2, A negative. It implies mod of A is minus A. So put in 1. We get minus A less than or equal to C, or A greater than or equal to minus C, or minus C less than or equal to A. So combining these two, we get minus C less than or equal to A less than or equal to C. So combining these two, this and this, we get minus A less than or equal to C less than or equal to C. A. So if we have taken mod A less than or equal to C, we have proved minus A less than or equal to C less than or equal to A. Now conversely, if minus C less than or equal to A less than or equal to C. Combining these two, minus C less than or equal to A less than or equal to C. So if mod A is less than or equal to C, we have proved minus C less than or equal to A less than or equal to C. Conversely, let minus C less than or equal to A less than or equal to C. It means minus C less than or equal to A less than or equal to C. Means C greater than or equal to minus A, we multiply with a negative number, C is greater than or equal to A. So in both cases, C greater than or equal to plus minus A. It means C is greater than A as well as C is greater than minus A. So from the definition of absolute value, mod of A is A if A greater than or equal to 0, minus A if A is less than 0. So in any case, C is greater than or equal to mod of A, means mod of A is less than or equal to C. So this proves the third part. But proof of the fourth part? Proof of the fourth part is simple. If we just, if we replace, in third part if we replace C by mod of A, we get the proof of the fourth part. So I think there is no need of writing it for proving. Let us look again. In order to prove fourth part, minus mod of A less than or equal to A less than or equal to mod of A. First we prove third part and then we take C as mod of A, and this proves the result. Thank you.